In this video, we will work on chapter 2 in class exercise 1 and 2. So as per the handout, we are here. So we are working on the problem for topics 2.1 to 2.4. And this is the vector angle handout. Before we do the problem solving, just a quick recap of what we have learned about the vectors. So in this example, there are 4 vectors A, B, C, and D, and each vector makes an angle theta with either x or y axis. So we need to find the projection of these vectors along x or y axis. So for that, we need to apply sine or cosine components. Now cosine always closes the angle. So if in this example, the angle is between vector A and x axis, so when you write cosine, A cosine theta, that will give the project the vector on the x-axis. So this will give the x component. While here, angle is between B and y axis. So if you write B cosine theta, it will close the angle between B and y and project the vector along the y axis. So go through this handout, pay attention to the sine and cosine terms. So A can be written as A cosine theta multiplied by unit vector I, that is for the direction, indicating that this is x component and this is y component. Same for B, C, and D. When we add two vectors, always add x component with x component. Never add x component with y component. We cannot do that with vector addition. So that's why we separate x and y components by multiplying with unit vectors I and j. Now, when we calculate the magnitude of, say, when we have a vector, let's say in this example, we have 4 vectors, and each vector has like the given x, y representation or ij components, and using this angle theta which is equal to tan inverse of y component divided by x component, we can calculate the angle for the vector. An angle is always measured from x-axis. If it is positive, then it is counterclockwise. If it is negative, then it is clockwise. So go through this handout, and again, once we solve the problem, this will make more sense. So we are now working on this chapter 2 in class exercise 1. That's about drawing vectors, writing the two-dimensional representation of the vector, and calculating the resultant of two vectors. So let's work on it. So that in class exercise is here. So question number 1, draw the vector f equal to 3i plus 5j. So here the x component of the vector is 3 and y component is 5. So we move 3 units along x and 5 units along y. So this is the point, and we need to draw the vector for that. So this vector f is 3i plus 5j. So 3 units along I and 5 units along y. So 3i plus 5j. Find the xy components of the following vector and its magnitude and direction. So this vector can be written as f is equal to 5 units and the direction is I, but it does not have any j component, so we will write 0j. We can calculate the magnitude of that vector with square root of x component square plus y component square, and that's 5 newtons only. So let's assume that the force is in newtons. And we can calculate the angle theta of this vector as tan inverse of y component divided by x component, and which is 0 degrees. Okay, so that's how we calculate the magnitude and direction of the vector. This is the concept that we apply to multiple forces and resultant force as well. Next one, write down this as a Cartesian representation. So this vector can be written as f equal to, it does not have any x component, so 0i, but its y component is going down. Now going up is positive for y, and going right is positive for x. So this is minus, so it can be written as minus 4j. Okay. For this vector, this can be written as x projection is 4 units, and that's in positive, and y is 3 units, that's positive as well. So this is 4i plus 3j and newtons. Let's find the magnitude and direction of the resultant vector for this problem. So what we need to do is we need to add these two vectors. Now we can use either graphical method or analytical method where we actually write each vector as a Cartesian representation and get the resultant vector. So let's write down f1 as a Cartesian vector. So f1 is 4I plus 3j. f2, and we make sure that we also write the units, Newton. f2 is negative along x because this is positive x, this is positive y. This is negative x and downward is negative y. So this is minus 3 units. So 3I plus 4j newtons. To find the resultant of these two, we need to add them together. So resultant force Fr is F1 plus F2. We can combine I parts together. So it's 4 minus 3 I plus 3 plus 4 j. So the final resultant vector is 1I plus 7j. The magnitude of the vector Fr can be calculated using this equation. Square root of x component square plus y component square. An angle can be calculated using theta is tan inverse Fry divided by Frx, where this part is called Frx and this part is called Fry. So Fr is square root of 1 square plus 7 square, which is 7.07 newtons. And angle theta is tan inverse 7 divided by 1, and that number is 81.9 degrees in three significant figures. So this is the resultant force magnitude and resultant force angle. That means if we need to draw the resultant force on this graph, we can actually draw a line at Fr, which the length of this line will be 7.07 from origin, and the angle that it makes with horizontal axis will be theta equal to 81.9 degrees. So this is how we graphically represent the vector on this chart. Okay. So there are different ways we can define the angle of the vector. So one option is we can actually directly represent vector by x and y component. That's what we have done here. The another more easy way is we write the magnitude and angle for the vector and then find the x and y components by projecting the vector along positive like x or y axis. So and the third way to represent the vector is using this triangular method. So what we will do in this example is we will write each f1 and f2 as a Cartesian vector. So we will write f1, f2 in this format and then find the resultant of that magnitude and direction. So this is what we are doing next. So let's write down f1. So 600 Newton is the magnitude, but it's at this direction, in this direction. How much of the 600 Newton is responsible for x-axis, or what is the x projection of 600 Newton? So this is really easy method for triangle, that x-axis is parallel to this side of the triangle, which has the magnitude which has the magnitude 3. You simply divide 3 with the longest side of the triangle, which is 5, and multiply this with the magnitude. So it is 3/5 of 600 is the x projection of the magnitude. So, and that is towards positive, so we write I. Along y-axis, this line is parallel to y-axis and that has number 4 on it. We divide that with the longest side to find the y projection. So it is 4/5 of 600 contributes towards y-axis, j. So this is xy representation of the vector. We can further simplify this as 360 I plus 480 J newtons. For second vector F2, we can find the projection along x-axis by closing the angle. So we apply cosine to close the angle to find the x projection, but the direction of the arrow is towards negative, so that will be negative component. So put negative sign, 450 is the magnitude and cosine 45 is the angle, and that's I. And to find the y projection, we apply sine of that angle. So plus 450 sine 45 J. So this can be written as minus 318.19. So F2, I'm writing that here. So F2 can be written as minus 318.9 I plus 318.9 J. Because sine and cosine 45 have the same magnitude, we get the same answers, newtons. Now to find the resultant of these two forces, F equals to F1 plus F2. So we can combine ith parts together. So it is 360 minus 318I. And that is 41.8. And it's 480 plus 318, which is 798.19 J. And that is the resultant force Fr of these two forces. And the magnitude of Fr is square root of 41.8 square plus 798.19 square. And that is almost 800 newtons if you round it to three significant figures. And angle theta is 10 inverse 798.19 divided by 41.8, and that is 87 degrees, 87.0 degrees. Okay, and that is the resultant force. And I recommend that for the resultant force you represent it graphically. Now since the both I and J components are positive, resultant force is in the first quadrant. So draw an arrow, write down the magnitude of the resultant force Fr, and indicate the angle that it makes with horizontal axis, which is 87 degrees. Okay, and that's the final answer. Then we move on to in-class exercise 2. So these are the different problems of in-class exercise 2. We will focus only on one of the problems. By the way, don't focus on this for now because there's a three-dimension problem. We will talk about that later. You can also skip this part. Let's focus on this one. So resolve each forces acting on the gusset plate into its x and y components. Express each force as a Cartesian vector. So there are three forces here, F1, F2 and F3. So it will be good if we draw a diagram, simplified diagram. So we define the x-axis here, define the y-axis as positive going up, okay, and write down the value of F1 as 900 Newton, F2 as 750 newtons, and F3 as 650 newtons, and define the angle, which is 345, and this is 45 degrees. So we need to write each force as a Cartesian vector. For F1 it's really simple because it's only along x-axis. So F1 is 900I plus 0j. F2 is 750 cosine 45I, 750 sine 45j, and they both are positive. For F3, x component is parallel to, like this line is parallel to x-axis, so it is 4/5 of 650 I, positive I, because it is, when we project this vector on x-axis, this arrow is going in the positive x direction. So x component is positive, and y component, when we project this arrow on y-axis, it will point down, so y component will be negative. That will be 3/5 of 650. And then multiply with appropriate unit vectors. So when we do that, we get this representation: F1, F2, and F3. And it has not been asked, but if we need to calculate the resultant force Fr, then we can add F1, F2, and F3 together. So it is F1 plus F2 plus F3, and just combine ith parts together. So it's 900 plus 530 plus 520. So that is 1950 I. And then for J, it is 530 minus 390. So that is plus 140 J, and bracket, and the unit is Newton, and that is the resultant force. You can also calculate the magnitude and angle of the resultant force using the equations we have applied in the previous class exercise.